I have posted in the Slack channel the link to the Rock and Roll All Night song. It's a joke. Okay. I have posted in the Slack channel the audio. All right, check, check. Clap your hands if you can hear my voice. Cool, we were already pretty quiet there, so that was pretty effective. So, how'd this warm-up go? Yay? Nay? Okay? So, pretty negatives. Pretty unanimous. Okay, so let's talk about this. What did we find hard about this problem? Why was it hard? Eileen? Sorry? Push to the approach. Okay, so Eileen said she had trouble with just the approach. Takia? Okay. Takia says, when I said Fibonacci was a hint, that was actually way more than a hint. She says that we still are struggling with the logic of Fibonacci. Yeah, that's fair. What else was hard about this? Why was it hard? Mateo?
Just the base case, because I feel like there's kind of two of them. One is when it hits one, the other is when it hits two. But obviously, if it hits two, it's still passive.
Okay, so Mateo had trouble really narrowing down on the base case because he says he feels like there were two base cases instead of just one. So that's fine. You're allowed to have two base cases. You can just write true if statements or if else. That's totally okay. That's a good concern though. What else? What else do we find tricky? Did we understand how this was like fibs? All right, well, if we think back to Fibonacci, we have this pattern. We have, yeah, Mateo?
I'm just interested.
How many people actually remembered how to do Fibonacci?
If you want to run your system, you can do Fibonacci right now. And that's what this problem is.
All right, so, yeah, I mean, that's an interesting point that Mateo's bringing up. He's saying, like, how many of us could do Fibonacci's right now? Well, not a lot, but we did go over. So it's pretty important that if we've gone over something and we still don't quite know it, we have to practice it. If you haven't written Fibonacci's 10, 20 times since we went over it, you're probably not studying that part effectively. That's like, these things we got to be able to nail. Because the pattern of Fibonacci's comes up a lot. So for this problem, this essentially was Fibonacci's, and let's just kind of start writing it. But we can remember that Fibonacci's went like 1, 2, 3, 5, 8, right? It's the last two numbers here. I can comment what a Fibonacci sequence looks like. What's the next number? 13. So it's always the last two. So when we had count ways, we were looking at, well, when there was one stair.
You increase the size of this a little bit.
Good. So when there was one stair, there was only one way. When there were two stairs, there were two ways. We were told when there was three stairs, there were three ways. Oh, gotta have room to type still there. Yeah, good idea. All right. Good? All right. Awesome. Okay. So it was the same problem. So we would start off with our cons. Stair count. It took in an n. And then we had our base cases. So, yeah, we're not?
I understand you like tested a few cases? How are you creating a rule based on like the few cases?
Interesting. Good question. So we're not saying how are we creating a rule based off of a few cases? How can we be certain that it is like the Fibonacci sequence? That's a great question. So some of that does play into like experience with these types of problems. Second, it's because of the way we're going to have to implement it. So we know that on every step, we can either go one step or two steps, and we want to see the outcomes of all of those situations as well. So let's solve it, and then if we're not sure, then let's try to iron that out more. So our base cases were the kind of things we were already given, right? So we were given, what can somebody help me with this one? Jenya? N is less than 2. Return n. Sure, we can do that because we were told we weren't going to deal with negative numbers. We could, if you were in an interview, you might want to discuss like the ability of like, should 0 steps be counted as 0 ways, or should we count that as like 1 step? Different people might have different thoughts. I know we all personally probably have like, oh, it should be no steps, or that should be 1. You know, that's going to be up to your interviewer. So, but for now, this looks fine. We can also say like, hey, do you want us to throw an error if n is less like a negative number, but they already said, no, just assume, and we go, all right, thank you for that. So I do need the parentheses. That's a great observation. I've been writing a lot of Ruby lately, which is no parentheses. The brackets you don't totally need them for like a one-line thing. I can put them if it makes it more clear. But not for a one-liner. It's somewhat standard to leave them away for a one-line. All right. Okay, so now we have to actually figure out how we want to move the steps. So I kind of think of my way as standing at the top of the steps. I don't really think of myself at the bottom of the steps. I think of how I'm going to go down the steps. And so I can either hop 2 steps down, or I can hop 1 step down. And for each one of those, I'll also want to count all the options from there too, because we're doing like this permutation-y type of steps, right? We saw with 3, it was like 1 plus 1 plus 1, 1 plus 2, 2 plus 1, right? That was given to us, I think. I'm just going off of memory. Oh, yeah. Sure, yeah, we can do less than or equals. I like that. That's fair. Good catch. So, all right, so let's think. So we can write return. And then we gotta call our function. We gotta call stair count, right? So we go stair count. And how do we move our n lower? Janelle? N minus 1, why? Because this is for when we go down 1 step. All right. But we have another case available as well, right? And that's when we go down 2 steps. So we got to account for that too. So we can go plus stair count. And what makes sense for this situation? Yeah, n minus 2. Great. That's it. Let's give it a shot. Now, if we were given the option of going down 3 stairs also, what would change about our problem? Who could tell me that?
Lots of stair content.
Yep, totally. So Leo says if we could go down 3 stairs, maybe we consider that in our base case too. but we could also just do stair count plus another stair count of n minus 3. It's just a pattern. There's a lot of problems like this. So let's give it a shot. We'll do stair count, and we were given the number 3, and we got 3. Cool. Let's do 5. Interesting. What's that about? There we go. 8. What did I do?
Sometimes it takes too long to focus.
Got it. So at 5, we did want 8 when we got to 5, right? If we do 8, how many ways are we expecting? I don't know, something, right? Maybe 64, 34, okay, I don't know. So it seems to be working. Questions on this? Renat, does that kind of help how we know it's like fibs? Not quite. Let's see, Davey?
I think the destination was a little. Oh, I see. The destination was a little misleading or confusing for me. The output makes sense now. Just looking at the output data explanation, I thought it had to be something on the line, like representing it as, 1, 2, 3, 1 step plus 1 step.
Yeah.
So we thought we had to visually see the different ways, not come up with just the number.
The upper low.
Mm-hmm.
I like it.
That'd make it a little trickier. So, because that's our base case. We've been given this situation. We know that if there's only one step, there's one way. And if there's 2 steps, there's 2 ways. We have to start from somewhere. And so we're starting at 2. We can't, anything beyond that, and we actually have to start doing math, kind of. Maybe you could use 3 if you wanted. Leo.
Yeah, we know that Fibonacci, the certain number is just a direct from some first one and the second one together, and that's what we mean that the more in the right, the larger. But for this problem, if we reverse the first two numbers, there's another possibility. Why the output of Fibonacci is just cover all the possibilities. It is I need to understand.
I'm not sure I understood the question. Can you?
Why the output of Fibonacci cover all the possibilities? For example, if you go 1, 2, and 2, 1 is different possibilities. Different solutions.
Yeah.
But for Fibonacci sequence, it's always 1, 2, 3, and 5. There is no 2, 1.
Yeah, but we're not actually looking at the steps. We're looking only at the number of ways. So we don't care about like visually seeing the permutations. We don't have to. We just have to look at how many ways per n, which is the same as the fibs. I know it's definitely tricky. We're not. 8? Why did it give 34?
That's 6.
So this is for 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps. So 6 should give us 13. Yeah. Here. Eileen.
So I'm not trying to figure out the density. So if you have say 5 stairs, right?
If we have how many?
5.
Okay.
Then we say 5 minus 1, 4 steps. Plus we say 7 4 minus 2, 2 steps.
Yeah, so we can whiteboard this and visually see it. I'm gonna do it on that whiteboard. So said for 5, right?
Yeah.
So I'm going to do staircase for SC, right? We go for 5. And so this creates a tree. It's like a tree of columns. We're going to go down the left side first and then the right side. So it's going to go SC of -1, so 4. And we have SC of 3. Then we have SC of 3. SC of 2. SC of 2. SC of 1. And 2 is already in base. SC of 2. And S of 1. Can we do 3 as a bit? Yeah, we could. Not necessarily. Yeah, it's fine. So we're getting all of these different columns. 1, 2, 3, 4, 5, 6, 7, 8. Okay. What did I just draw? This is the function making calls recursively. So we would say, is n less than or equal to 2? We would say no. So we have to go into our deductive step. So we say stair count of n minus 1 plus stair count of n minus 3. Then it goes, all right, is
That's the second line is, right?
into function.
This is all it is?
Yeah, and so then it creates a new function call and says, all right, is 4 less than or equal to 2? No, so it has to do that return statement. So it's going to say stair count of 3 plus stair count of 2. And it's going to go, all right, is 3 less than or equal to 2? No, so that's stair count of 2 plus stair count of 1. So this returns, what's this return? 2, and this returns 1. Right? So then this becomes what? This becomes the number 3. S of 2 returns what? 2. Okay, so this becomes 2. What's S of 4 become? 5. And we go over here, we still have to evaluate this side. So we go S of 3. Is that less than or equal to 2? No. And so we go S of 2 plus SC of 1. So this is going to return what?
2.
2. And so this becomes 3. 3 plus 5, 8. Right? Questions on that? How this is working? So, all right, if we look at this, what do we think the time complexity is? Yeah, it's pretty terrible. What is the time complexity? Take a minute. I'm going to let everybody have like a minute to actually process it.
Look at this, right? Like, look at that. Look at how quickly it's expanding. And think about, like, what if we were giving an input of, like, 10,000? What would happen?
That's a 3 and that's a 10. 4 is greater than or worse than 2. the tenth iterations and return staircase. N minus 1 plus staircase n minus 1. All right, who can tell me the time complexity? What do we got here? Someone who hasn't spoken today. All right, let's go, Jonathan. What do we got here? O of n squared. Okay. One. You can go O of n. There's no wrong answer. I mean, there isn't. I mean, you just have to, at least if you have to defend it in this game. You're going to give someone a time, but you're always asking why.
Alright, so O n squared has larger chunks, more longer things.
Okay. So he says it's O of n squared because for each number we get, we're going to have to do like that times many more operations. Okay. David, what do you get?
Yeah, I mean, same, more so because for each function call, we're going to that call.
Right.
So instead of being linear, it's just one more.
Okay. Yeah, that's interesting. I think I would go with 2 to the end. I'm wrong, right? Trick up, right? 2 to the end.
Oh, yeah. Yeah. This is,
So why is it 2 to the end? So when I have, for every call, I have to make 2 calls, and those in themselves may be making 2 calls, continuing. So at 5, I'm doing, it's got 2 calls, and this has got its 2 calls, and this has got its 2 calls, and this has got its 2. So every time I put 5 in, I have to make all. So if I do a 6, I'm going to have all of this again, plus all of this again.
I have a question.
Yeah.
What is the difference between what 2 to the n looks like and what n squared looks like? Yeah, but what's the difference between what it looks like? I know that one is. Okay, well, it's real cool, but what I'm actually wondering is like for an O of n squared algorithm, what does this call look like? No, I'm not worrying about that. I think that we can.
You mean the solution to this problem? Or
Not a solution to this problem, right? But like I'm wondering when this separates into 2 and then it separates into 2 and then it separates into again. So I'm interested in seeing like what if it's separated in n, right? That's what I'm interested in seeing because I'm gonna be real. I was a little bit confused about the difference between 2 to the n and n squared. I know that one of them was less efficient, but I didn't fully internalize it.
I think so, that's good at the end, the coefficients and the difference.
Is what?
When you have like 2 to the end or anything like that, the coefficients don't make a difference. Well, the exponent.
Yeah. Yeah, no, I get that. I just can't picture it. Right? Or I couldn't do it. So I'm interested in hearing you elaborate.
Is this what you mean, Rick?
Yeah, something like that. Yeah, one of them is huge. One of them is not as huge.
So if we want to make it more concrete in numbers here, let's try some more numbers, not just 900. But let's start with just like 10.
So which one is which, by the way?
So
Then n squared.
n times n squared, 2 to the n. So if I did 30, somehow I kept all of that. The difference. Those are pretty big different numbers, right?
So 2 to the n is worse.
2 to the n is significantly worse than n squared.
What does a
Okay.
double
Power 2. Questions on this? And why 2 to the n is so much worse? Yeah, Takia? What? Oh, okay. What was your question? Hey, there's a lot of side chatter, but we're still in class. Takia? How is 2 to the n worse? Well, we're going to just even look at it with the math. So n squared is n times n. So if we did 30 times 30, we get 900. If we did 2 to the n, which is 2 to the power of 30, we end up with that number. Janelle?
I'm still trying to figure out how you guys are getting time. Like, I understand once you explain that it's gonna go through many steps in order for you to get an answer. And then from the time you get the answer, it takes a while for you to get the result. But how can you look at that and say that that's n already 0, 6, 3?
Great question. So Janelle's saying, how do we know the time complexity of something? So this kind of goes back to that big O conversation, which is if the number of operations is consistent with the size of n as it changes with n. Like if we give you an array of 10 things, you're going to be doing 10 operations. If we give you an array of 200 things, you're going to be doing 200 operations. If I give you 1,000 things, it's going to be 1,000 operations. This is linear, right? So that's O of n. Now, if I need you to compare every element in the array with every element of the array, you're going to have to go 0th index, 1, 2, 3, 4, right? 1 index, 2, 3, 4, 2 index, 3, 4. That becomes n squared. So if I give you an array now of 10, you're doing about 100 operations. So that's how we're making those calls. Constant means no matter what, it's the same amount of time. So if I have a function that takes in 2 numbers and it just adds them together, it doesn't matter the size of my n or how big those numbers are, because the math is a constant speed. Does that help clear that up, Takia? Fibonacci's implementing it this way is 2 to the n. Oh yeah, but there's better ways to do it. Crispina.
Well, there's 2 graphs. The one that's to the end of the one that's closer that way, right?
2 to the n is time complexity of the whole function. That's a visual representation of how the function is running. So we can.
Which one is which? The one I'm at.
So the top line is when we first invoke the function with the number 5.
Or means on the graph.
Go on further to that. To the
The graph.
There's only one thing up there. Oh, you're talking about this little.
so
Oh, 2 to the n is, yeah, the one on the left. Got it.
Is that like the worst time complexity, or is there one that's worse?
I think there's ones that are worse than that, but that's, I mean, there's n to the n, right? I mean, yeah.
So this solution is constant, or is it 2 to the n?
This solution is definitely not constant speed. It is 2 to the n. Constant is the fastest thing we can do. Yeah, indexing is a constant operation. Math, is a constant operation. Comparison, like that, like less than, greater than, that's all constant.
Constant is O of 1.
O of 1.
What's O of n?
O of n is a linear relationship. So if I have 10 things in an array, I have to do those 10 operations. If I have 100 things in the array, it's 100 operations. If I have 1,000,000 things, it's 1,000,000 operations. It's changing directly with the size of n. Chris?
What about log?
Log. Okay. Log of n is better than n because it's getting, pardon me, it's getting half. It's like halving things. So if I give you an array of 10, we go to become a 5, to a 2, and then the 1. If I give you an array of 100 things, which is 10 times 10, right? I'm only going 10 to 50 to 25. So I've only had to do about 2 more operations there before I'm in like 12, right? And then I'm at 6, 3, 1, right? So it's cutting down. It's like going through a phone book. So instead of going from page A all the way to Z, I don't know. I feel like math, they would say Z. It's like starting in the middle and going, okay, the name I'm looking for is actually in the first half, so I'm going to split that in half. You'll find the name faster that way. Winter, was that a question? Oh, okay. Keep going. We're on a roll here. Are we feeling better about this? Yeah, Mateo.
So just to confirm that stair count, all it was doing was trying to tell us how many ways we can go up or down the stairs by 1 and 2.
Yep.
We're not trying to solve a problem. We're trying to get that part of it.
What do you mean by that is the problem?
I thought you had to return it.
No, you're overcomplicating it. Yeah. All we had to do was find out the number of ways. We were just looking back for an integer. Yeah. Good question. What are we looking at there, Reed? N squared versus 2 to the n? Looks pretty crazy, right? Especially if we consider that his other one is like not as deep.
Right, n squared is only going to be like 2 calls deep. 2 to the n is going to be n calls deep, but we're only doing 2 calls per call, right? So as this gets larger, both of them will get significantly larger, right? But this one will grow at a slower rate than this one. Yes, significantly as the numbers get much, much larger. Yeah.
What did you say the squares of the I'm going to see those.
Right, n squared has like it's going to take longer to grow. Why did I say it's going to take longer to grow? Because as n grows, what I'm saying, as n grows, these get bigger, right? By like n times, right? But for 2 to the n, they get bigger. How much?
It's a whole extra row at the bottom.
Yeah, 2 times. Yeah, it has a whole extra row at the bottom rather than just adding 1 extra pip to each of these things.
So if you're looking for something more concrete, just think about the number 30 there, and we can see the humongous difference in numbers. Yeah, Christina.
So this guy right here has N, right? Right?
I guess.
It's 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
So if we run this with a number like 30, we'll see that things really aren't so cool. Well, that wasn't too bad, right? But let's do 35. All right, not too bad. How about 40? So we can see how much that's ramping up now, right? It's starting to take a lot longer than what we want. I mean, we just like 40 wasn't that slow, right? But 45 is super slow. Yeah, so I'll see you tomorrow. So there is a better way to solve this, right? We can solve this essentially in n time, but we have to use objects. Don't know if we've got time to go into it, Mateo. Yes. The difference between 40 and 45 was insane. Hey, that's our number. That looks pretty good, Crispina. That's right. We're just doing so many operations. We're probably doing, well, whatever. Let's see how many operations we're doing. We're doing 2 to the 45. So we did this many operations. Doesn't even fit in the screen. So that's a lot. I mean, we did that pretty fast, but it's certainly not the greatest thing in the world for us. So the question becomes, well, how can we improve this? So I can either go over this now or we can move on to the next thing. What do we want? Do we want to see how to get this better? All right, so we can do something called memoization. If we don't fully understand it by the end of this, that's okay, because I do want us to learn some stacks and queues today. So memoization is, have you ever heard of a memo? I didn't get the memo, right? That's like a little note or piece of information that's being distributed to everybody so that we know things. So with memoization, we can look, if we go back to our thing here, I don't know where I need to mark this. That's pretty cute. Oh, they're in my hand. All right, so let's do a little bit more of an extreme example here. I'm just going to write the numbers instead of the actual function call because it's going to be a lot faster. Okay. So let's just say I had SC and I had 7. Right? We have 6, 5, 5, 4, 4, 3, 3, 2, 2, 1, 2, 1, 3, 2, 2, 1, 4, 3, 3, 2, thank you, 2, 1, 2, 1. Cool. Do we see any redundancy in here? Why? Why does this suck? We're not? Oh, it's on?
Oh, so you just take the value and say this is right?
Yeah, say it louder. No, you can't say it louder. I will say it 10 louder. He said so we can save the value somewhere. Yeah.
I'm just going to say that the edges of the tree all.
Yeah, exactly. So the edges of the tree all run the same. The way we know functions evaluate is as soon as a function gets called, it goes into that function, right? So we're actually going to move down the left side of the tree first, right? Are we aware of that? And then, so it's going to go here, and then it's going to go there, and it's back up, and evaluate that, and it's gonna go down, up, that. That's like the order. So knowing that, we're gonna make all of these calls. This, and then we're gonna save this number. This is gonna be our 3 number. So then when we go up to here and we go to the evaluate, we're gonna see 4. We're gonna save our 4 number. And when we see our 3, we're gonna go, okay, we don't need to make these calls anymore. We already have the 3. And then we go back up to 5, and we get to save our 5. We go over to our 4. It goes, well, we don't need to make all these calls anymore because we already have the 4. So now we're going to save our 6. Then we start evaluating the other side, and we go, well, we don't need to make any of these calls anymore because we've already got our 5. Does that make sense? Do we see how much faster this could potentially be? What do you mean it does? No, we can make it work. Definitely. Mateo,
Is that O?
yeah, I think this is O of N, because these would be constant lookups.
What's our O?
O of N. These are constant lookups, but we still have to do it for every N. So let's write this. Let's see how to write this. We don't fully understand it's big, we've got to get to stacks and queues. But we can do a little bit here. And so instead of just passing in N, we can pass in an object that we're going to keep passing on, called memo. That will default to an empty object. We could even get more fancy if we wanted to and put default values in there already and then not even need the base case, right? Because we could just say, if we know so I'm going to avoid something a little bit annoying. So I'm just going to say if we had 0, it's going to point to 1. Okay, I don't think we're ever even going to get to 0. I can say at 1, we're going to point to 1. And at 2, we're going to point. What happened? Okay. At 2, we're going to point to 2. Right? That's what this is essentially covering. All right. Yoink. All right. So now we've got this memo that's been defaulted here. We still got to do a base case. So we got to check if our memo already has that number in there. Right? So I can say if memo at N return memo at N. Cool. Is that fair? This is now our base case. Nilene?
So our old base case wasn't.
Our old base case was fine.
Our old base case does not support students phenomenon.
Well, we could have made multiple base cases. Well, we could still make it return 0, but then we just have to, change. We can make it 0. We can just say if memo is not equal undefined. There you go. I was just avoiding that little thing because it's going to come back to 0 possibly, but that's fine. Our base case from before is still okay. So now we've got this base case that's checking to see if our memo already has that in there. And if it doesn't, we have to do an inductive step. And so we have to still return. And we can say memo at N. And we can just say that's what it equals to. So now, if we pass in 4, it's not already in there. So it's going to say now at memo at the key of 4, we're going to call these. And this is going to say, all right, it's memo at, we have to pass in memo now. Ay, ay, ay. Can I make this bigger still? Okay, do we see this? Okay, we see this? So now when we're checking, we're saying, hey, stair count at 3, memo, we go, all right, well, there isn't a 3 either. And so we go back and we say, all right, staircase at 2, and it says, all right, that's 2. And then we go over to here, and it says this one was at, should be 1 now, right? And we say, all right, 1, memo will go, okay, 1, so 1 plus 3. So now memo at 3 is equal to 3. And then we come back to here with 4, and it adds it up. So it's essentially what we're writing there. We're just saving the numbers as we hit. Yeah, so now when we check on our stair count of 45, let's see if it still kills us. No, I'd say that's quite a bit faster. Right? I'd say that's a lot faster than the old way. Like maybe 1,000 plus times, million times faster. But yeah.
So this looks a little bit also like what's that? Reduce. Is that like is that like a memoization?
Not really. I don't know. That's not how I think. I mean, if it helps you think of it that way, I don't know.
Well, I guess I'm trying to get at this.
I don't know. I don't really understand the situation. Maybe. Sorry. In my work, I mean, reduce is sort of keeping track of things. So yeah, maybe you're talking about like with the accumulator being the memo. Yeah. Yeah, I guess I could see that. Yeah.
Okay.
Davey.
How is it that, is it just a keyword memo that allows?
No, memo's not a keyword. I'm just calling it memo.
Okay, so then, how is it that each function call goes to go down a certain, I guess, or up the call stack up to a certain point and not like start?
Because we are mutating our memo. They're all referring to the exact same object. The call stack always will go down the left.
Always?
Yeah, because as soon as it hits whenever JavaScript hits an invoked function, we go into that invoked function.
Right. Oh, so you're saying, so then before we did the memo, it would still go all the way down and then do each one?
Yep. It will always go all the way down and then as far up as it needs to before it goes. And then if it can go left again, it will. As soon as it hits that function, we're going into that function.
So once it gets up,
Yeah, so by the time we get over to 5, we've already gone all the way down. And since we keep mutating that memo and adding it to the object, by the time we get to 5, it hits our base case and it says, oh, doesn't equal undefined equals 5. Let's just return that. Or whatever 5 is. I think it's 13 or something. This is a hard concept to wrap your head around, but it's, as you can tell, it's super important for efficiency stuff. If you are in a whiteboarding interview and they have you solve a problem, and then if it's the right kind of problem and you can memoize it, it's going to look very good. Because a lot of places have a lot of users and things. Johnny.
Can you put a console log between lines 4 and 5 that actually traces memo practice?
What do you want?
A console log
Of what?
memo practice. Within the brackets, above
It was okay.
process to treat.
Well, yeah, we can see it's doing the math.
Can you explain that? Like, waves going down the left hand side?
Yep.
One way, right?
Exactly.
Do a small one. 45, maybe like just 5.
Cool. Should we do stacks, cues? All right, let's take a 5-minute break. Be back by 11:22. Good morning. How you doing? Mm-hmm. Mm-hmm.
You know, when you have the n minus 1, say the n minus 1 common number. When you have the common number, what does it mean?
So I'm passing in a second argument to the function.
Where is it gonna go? The second argument is just isn't gonna be computing anything, it's just gonna be storing whatever was made, whatever it said it was gonna do, which is store.
Yeah.
So it's not really gonna affect anything, it's just gonna be.
Well, it passes it on. Yeah. We're passing on this same variable every time we call. So if we make adjustments to it, they all can see it for the future.
Thank you.
No problem. Good question.
So, I mean, not a lot of them. What's the everyone who sees it, points out what's wrong with it.
It's small
I
hair.
did put
Otherwise,
the,
yeah.
be able to just point out.
Oh.
This is true.
Yes.
Exactly. I just realized that.
I'm gonna bring you to the next show, and then you can twist your ankle.
So there, everybody twist their ankle.
No, just me. Someone's got some bloody nose. I'm glad I didn't get ours. I don't know what's better, bloody nose or.
You want me to twist my ankle? I twist this one. All you see is metal.
Why? You have a ankle replacement.
Still having it.
What happened?
No, I broke my ankle at one point.
That's good. That means you
I
can't.
could jump pretty high.
Get a bionic ankle.
I do look faster. But this I have 5%. I try to walk speed walk.
Listen.
Oh, they're one security, the other guy in the fire. Just up to you. It's my talking.
You're like, you know, I have metal in my body. You want to guess what?
Yeah.
I'll be on your team.
Yeah. You gotta twist your ankle.
Yeah, I got it. You guys didn't say hi. Why do you look so cool? That's not your normal. That's your normal. I've seen. Are you guys going home? Home.
Especially with that ankle.
No, for I'm like, let me get
All right. Clap your hands if you can hear my voice. Clap your hands 2 times if you can hear my voice. Yeah, let's get ready to get back into coding, everybody. Jenny, can you close the door real quick while you're walking by? I'm definitely loud, and I know we're all loud because we're going to be jazzed up and cheering and pumped up. Today we're going to learn about stacks and queues. All right, let's get stocked up and let's get ready. So, what's a stack? So stacks Great question. So stacks are another data structure. We've got arrays, we've got objects. Now we're going to talk about these things called stacks and these things called queues. Now stacks and queues aren't too crazy, hopefully, because they're pretty similar to arrays. And when we make our own, we'll probably implement it with an array for now. Eventually we'll probably use like a linked list, but we don't know those yet, so definitely won't be doing that. But for now, we'll start with an array. So basically, let's talk about stack. There's a nice little acronym, which is like, it's called LIFO. So basically means last in, first out. Right, I should have gone to Trey for that. Sorry, Trey. So can we think of an example in life where the last thing in would be the first thing out? Crispina.
Last hired, first fired.
Wait, what is it?
Last hired, first fired.
Last hired, first fired. That's dark. But totally great. All right, let's get back. I know none of us have jobs right now, and that's not true. A lot of us do have jobs. And that's one of the reasons why the course is so demanding. But that's a great one. Let's go. Who do we got next? All right, Trey.
I would say
Check-in baggages at airport.
it goes into the airplane. The person who goes in the airplane is always the last.
Okay, so packing an airplane, we could say. So Trey's saying packing an airplane, we're throwing in a suitcase. We're throwing 3 suitcases. We're going to unpack it in the same order. Cool. Jenya? Packed elevator. Definitely should be like that. Winter?
Milk.
Milk. What's
At the store, like the first one that they put in is like the one that expires first, so they push it to the front.
interesting? So that's going to depend on where they're filling up the milk. Because some of those milk places they fill them in from the back. So, I'm not going to repeat that one just in case. But if you understand it, that's the most important. Abed?
If you have a long drive, maybe only one car.
If you have a driveway or something? So like a long, narrow driveway. Okay. That's cool. Great example. Diana? Pringles?
Yeah.
Okay, so she's saying Pringles. I guess she's also putting Pringles back into the container. Pretty interesting. I'm not going to borrow Pringles from you. Johnny?
You're a waiter. Stacking plates.
Plates, classic example, right? As a waiter or even just at home, right? We have like a stack of plates. We put them on. We take them off. The first one. I don't know about you guys, but at my house, I definitely don't know what my bottom plate is. I use 2 plates. I literally have no idea what the rest of them look like. They could all be full of swears. All right, what else? We got any other ones that we want to share? All right, we got trays, right? Like cafeteria trays. The wet ones on the top, and it's always the first one taken. Okay, how about, let's see, what is like an example? So this is similar to the back and forwards on a computer. When you're on a website, every time you go to a page, maybe it goes, when you leave it, the page that you were on goes into a stack, and then when you click back, it pops it off the stack, right? It's actually 2 stacks. Interesting. We might use this for reversing a word or syntax checking compilers. That's what's in the notes. So stacks have some very specific methods. They have push. Sounds familiar to anybody? Push? Hopefully it sounds familiar to everyone. If not, talk to me after the lecture. We will make sure it does. We have pop. Does that sound familiar to anyone? Pop? Yeah, okay. We have peak. What do we think peak might be? What's peak? Okay, so Kia says taking a look. Yeah.
I would say like observing the data.
Observing the data. Interesting. Okay. Yeah, so peak is what we're going to see next. What's next to come? We don't actually get to see the whole stack. We only just get to see what's if I'm going to grab one from the stack, what am I going to grab? Is it a handful of grapes? What is it? Mateo. Just shows you it. Just a little peek. Peek, peek, peek. We're not. Can you be louder, please? What am I referring to as a stack? So the stack is this new data structure that we're learning. I don't know how to visually represent it here, so I'm just gonna draw like, yeah. So this is essentially our stack. It's last in, first out. It's a LIFO, and we've got like this stack here, and our programs run a lot like this too. Maybe we've seen like stack overload or stack trace, and we look at the stack. That's like the order that it happens. So if we were putting on, if I put on a plate, I'm like, all right, I'm done with this plate. Let me put it on here. And then my wife says, go get me a plate. All right, I just put one away. Let me grab that one, right? And then she finishes it. You watch this play, but yeah, and then I put it back on the top. And then I realize I'm hungry, so I take it off. And then, you know, a friend comes over, I guess, and I give them another plate. I really like having people over at my house. So that's why I only use 2 plates, my wife and mine. So that's, you know, that's how that's happening. That's a stack, and when we're doing it with, like, it could be filled with anything. It could be filled with numbers. We could have 7 here, 14 here, 6. If I call stack.peak, what do we get back? 6. Okay, and then if I say pop, what do we get? 6, okay, and then this leaves. And then if I say stack.push grandma, what's next? What happens? Yeah, so now this has my my grandma. Okay, and then I say stack.peak, what do I see? I see my grandma, yeah. And then I'm gonna, my grandma's a little lonely, let's pass on grandpa, stack.push. What do we get? Now we get grandpa on the top. He's got a key. Yeah. All right, grandpa died, let's pop him off. So I say pop, grandpa's gone. I pop again, sorry grandma. I'm only down to 1 grandma left. She's hopefully down here in the stack. We're not gonna get to her. But, so this is our stack. This is like this data structure that we're gonna be using.
So is it indexed?
So no, stack is not indexed. And so when we implement it, we might use an array to implement it under the hood, but we might also use linked list. We don't really necessarily know how it's implemented, although we're going to implement it. Mateo.
So it's not just like an array inside of it?
You can think of it like that. It doesn't, but it's not necessarily an array. It's a data, it's its own data structure that only has push, which sounds array, item, pop, peak, and I think there's one more, is empty. What do we think is empty is? What's this return? Yeah, right, this returns a Boolean. And what's it checking for? Whether or not it's empty. So we're saying, is there anything in there? If there is, we return false. If there's nothing in there, if there is something in there, right? 14 and 7 right now. If I say, is this empty? But nope. And then I say, all right, pop, pop, empty. True. Great. We're testing.
With that example, 14 and 7, do you have access to 7 in your stack, or
no? We'd have to pop
everything else, and after that?
Yeah, but we could potentially might have another stack that we pop things into so we can access things. And that starts to get a bit more complex. We'll eventually get to, but I don't know if we'll hit that today. We just want to know the qualities of this data structure, why we might use it, such as like keeping track of the history on a web browser, how we might see it in real life. Mateo.
This question pop is like the array that is
Yes. Yeah.
If you're reading an article, yeah, it's differently. It's like building a stack.
Yep, because then when you click back, right, you can keep going all the way back until you go, I don't remember being there. Yeah, yeah. But then you can also go forwards, right? So when you go back, you're usually taking what you're currently on and putting it on another stack. And you go back again and you put that on that stack, and then you go, all right, I actually want to go forwards. So we go back to here, we pop that back into history, and now we're in forwards. Sorry for the screencast, it's all on the whiteboard and stuff.
Where's that like, depending on the context that you're talking about, is vertically?
I don't think so.
So like, I heard people say like, what stacks do you work with?
Oh, got it. So, great question. So Davey's talking about when people say, what's your stack? Or like, what stacks do you work with? They're talking about the full stack application. So they're talking about what front end, what back end, like, are you using? So the stack I learned specifically was a Ruby on Rails back end and React Redux on the front end. You guys are learning Node in the back end and React Redux in the front end. Essentially, yeah. It's just called like, what's your whole back end to front end? Like, what are you most fluent in or whatever?
Oh, also, we know about Redux, Galilei, Backs.
Now we do, yeah. All right, so let's implement our own. So we remember how to make a class, yeah? So I'm gonna give everybody 15 minutes to implement their own stack. So if you need a hint, right, you start with the word class and then write stack. Your constructor function might make an array or something that like a data structure that we already know and are comfortable with. And then we're gonna have those 4 methods on our stack class, right? We're gonna have push, pop, peek, and is empty. All right? Any questions? All right, let's make it. Yeah, if you've already seen the solution at one point, that's fine. Just don't look at it now. You're right. It's all right. Okay. You're right.
Yes.
Created a new class. Oh, that's something else. Why? Yeah. We're running our own. So to get that. Yeah, that's all. Oh. Yeah, if you want to work in pairs or something, that's totally fine. Heat and is empty. Yeah. All right, clap your hands if you can hear my voice. Clap twice if you can hear my voice. So we're gonna have some more time to work on it. I'm just gonna nudge everyone in the right direction here. So if we were working in REPL, which you probably shouldn't be, right? I would write class. What's our class called? Stack. What do I do next? Curly brace. What does it need? Constructor. And then when we start a brand new stack, we want our stack to be empty, right? So, and we need to have, and currently the only data structure we have at our availability is an array that might be able to keep order. So we're going to say this dot array is equal to an empty array. Okay, now I saw a lot of us got here because I think we accidentally read the GitHub and then we seem to get really stuck. So the functions we have on a class, the methods available, go next after the constructor. So if we had a push, we would write push, and then it would take in something. So value, well, and then something would have to happen in order to keep our array behaving like this stack. Okay, you have another 10 minutes, and the same pattern kind of for all of them.
Oh, and the return.
This got hard to really just underline. I think you can maybe use the language here, right? Because like it's not going to be right? But yes, you're one transaction. And this peak show, like this peak up and I think it's really here, right? Show the beginning here. Okay, good.
Is there a way to?
Is there a method to show the beginning of your end?
You show.
I mean, like the reason why I didn't know how peak is I always just did like array at 0 or array at the rate of No, what you would do, right, is you would just key into the array and add the rate on length. Star. This does keep this, but
That's just the rest of it.
Yeah, it's not even a method, it's just a pattern to see the last index that you're in. Okay. And maybe JavaScript has a method called key to make that available to the array, but this is like right?
Here, right? I can see it for your patterns. I can see what you make.
It doesn't have to be.
What? Okay.
This one is showing what's this one.
So literally the only problem with this, you're like doing just fine, right? Literally the only problem with this is that on line 11, right, when you go let blank equals new stack, you're invoking the class stack correctly. You're creating a new stack, right? But when you console log stack invoked, right, that's not the way that we create instances of classes. What I would recommend you console log is blank. Not even invoked. It's because it's just a variable, right? Blank dot push. So it would be after you declare blank, right? Then you go blank dot push 1 and your stack should be the integer 1. So you understand what we're doing? Oh, so here's what I'm thinking of, right? Like when we're talking about classes, they're just like functions, right? In that we have defining them, right? Which is where we do the curly braces to define them, right? And then we have invoking them, which creates an instance of that class, right? So you just invoke that function here, which makes an instance of it, but it doesn't make sense to put curly braces past that, right? Because that's the syntax for defining. Yep, on the next one, yeah. Right? Because blank is now an instance of the stack class, so you just have blank to do whatever you want with it. Any functions that you define on the stack class, blank is going to have access to it. One. Yeah, so your stack now has 1 on it, right? Because blank is an instance of stack. You can make another instance of stack, and it wouldn't have that 1 on it, right? Each of them is a separate. This is just defining the behavior for how it works, right? It's just like defining a function for right? Except for what that function produces is an object. Yeah. Yeah, so I think that you have a good understanding of what the stacks are and how they work. It just seems like the kind of gap here is the ESS classification, right? And sort of what the classes are and how they work, right? So classes are basically just syntactic sugar for defining an object and putting a bunch of functions and properties on an object. right? So just think of it that way, right? And then whenever you say new that, right, what you're saying is like, okay, I'm gonna make a new object, right? And that object is going to have stuff that I can change around and like work with, right? But frequently, right, we declare a new class, like a new object from our class, like once or twice. Right? An object is just like another way for organizing our code, right? Functional versus object oriented. Right. So I think the big thing here, right, is like thinking about how to actually use the classes we define, right? Because I think a lot of people are thinking that like when we define a class, when we say class stack, and we define a bunch of behavior on it, what we're doing is we're making an instance of the stack and making it work, right? But I think that's sort of similar to the thinking that we had early on, that when we're defining a function, we're like making that function go, right? Whereas now, right, what we have to do is we actually have to invoke the function after and do anything, right? Classes work the same way. So for example, in tic-tac-toe, right, what you do with your game after you define it, right, is you go new game, and then you use game.play. Right? So that I think is a really important association that we create, that we can create between functional and functional programming and programming with classes, right? That classes are just like a plan to do something. They're not actually doing it. They're a plan to create an object, and then we have to create an object out of it by using this thing, right? Yeah. So maybe code snippets. Yesterday, yeah, I shared like I use this thing on the DOM, like a very basic version of it, and expanding on that is a great way to not only study object-oriented programming, but also like pepper DOM there, which I think is like super great because not only because it gives you all that practice, but also because when you finish that game, it's like a thing that you play in the browser. It's so cool, right? You know, on your GitHub, on your resume. It really is. We're going to do more pair programming, and I think that was a common issue with people's pair programming, right? Yeah, so I really... Right.
All right, clap your hands if you can hear my voice. Clap your hands 2 times if you can hear my voice. All right, let's get through this so then we can also learn queues quick, which shouldn't be too hard because they're pretty similar to stacks. And then we will be doing whiteboarding. So, push. How can we push an element into our stack? Somebody help me. Janelle? Yeah? Pass in the value. Perfect. So if we want to return something, we could throw in return. I don't know if our push needs to return anything. I guess it depends on how we're implementing the stack. Maybe I'd want to return true if it was successful. Maybe I wouldn't. I don't know. For now, I'll just return nothing. I'll just trust that it's working. So then we have pop. Someone else help me with pop. Let's see. Max. Okay, return this dot array dot pop. That looks good to me. Let's do peek. Now I saw a lot of people write this. We got into the theme. Is there a peek method on the array? On arrays? No, right? So we can't do that. We're actually writing this one. How can we do it? Trey? Array.length -1 makes sense to me. We better return it, as that's the whole point of it. Questions on this so far? All right, and then we got, let's do our is empty. How do we know if our stack is empty? Muna. Nice. So she's saying we can just look. If our array is 0, our stack is 0. So this works, right? Parenthesis where? Wrap this? Oh yeah, no, I wouldn't need to do that. This will, because we're checking here, this is going to evaluate to a true or false. That's a great question. Although if you put parentheses in it, it wouldn't hurt it. Are we good with, yeah, JR?
So for the is empty,
yeah, you could do that. So JR is saying he didn't do this comparison. He knows that 0 is a falsy value, so he went like that. That's clever. Totally could do that. We good with stacks? Okay, so let's touch queues. So queues are pretty similar concepts here. Instead, they're called FIFO. Trey. That's right. First in, first down. What are some examples of queues in real life? I don't know, maybe. Alex? When people wait for the microwave? Yeah, so any kind of line, right? That's why in England they call it the queue. Like, did you get in the queue? Listen, you're in the queue, right? Going into a nightclub there, right? We got that muscle bouncer and all those people waiting behind the velvet ropes. All right, well, maybe Jenny has a lot more success at a nightclub than I do. Yeah, maybe you can go to the front. I am in the back. And that's A-okay with me. I don't like to leave my house, actually. I'm pretty into the house. Okay, so first in, first out. FIFO kind of sounds like FIFA, but it's different. And we've got some specific queue methods. Similar to push pop and all that, we have something called NQ. I think it's spelled like that. NQ takes in an item. And so in our stack here, or it's actually a queue, sorry. I'm going to move things in this order. So I want to take Q and I'm going to NQ my grandmother. Right? So she goes right here. Just actually got kind of further here. And then I'm going to NQ the number 7. Right? And so then I have something called, I want my grandmother to escape. I don't want her to be prison there forever. So I've got a DQ, not to be mixed up with Dairy Queen. I'm going to say hey, Grandma, you want a DQ? And she's like, I love blizzards. So she gets out. And now in our front of our cube, we have 7 just moves over. And now we've got 7, right? And 7's in there until 7 decides, oh, there's a holiday special at DQ and I'm going out, right? So we got NQ, ice cream branch hasn't been invented yet, and then we got DQ, which we all love. And that's how we're all going out to DQ. That's how you can remember that. So we got some fans of DQ. We also got peak available to us here. That looks pretty familiar. We know peak. We want to peak it up. And then we got is empty. Also looks very, very familiar, hopefully. If you were here for the last hour, really should look familiar. Right? These two especially, and these are just kind of fancy names, right? Instead of it being push or pop, we just got NQ, DQ. So let's play around. We got our Q. I'm going to say NQ6. What happens? Something might happen. What happens when I say NQ6? 6 goes in. 6 has been NQ'd. I say Q peak. What do I get? I get 7. That's the next one coming out. But my Q stays the same, right? Okay, Q is empty. False, great. Yeah, we're going to use false. Okay, let's go to DQ. What happens? 7 comes out. That's what's left. All right. DQ. What happens? 6 comes out. It's empty. True. Peak. Undefined, maybe. Okay. NQ. Grandmother. I'm very close with my grandmother. Let's peek at my grandmother. Peek. Yeah, we've all been there. All right. Grandma's getting hungry. She goes to DQ. She's out. Is empty. Perfect. Questions? All right. Grandma would be proud. So we're going to do this in a strict 10 minutes because I want you guys to have some time to whiteboard, and I think we can do it in 10 minutes. Just like we did for stack here, I want you to make a Q class for quiz questions Q, right? Numero uno, let's go. 10 minutes, and it's going to have NQ, DQ, peak, and is empty. Should be a lot of crossover.
We didn't follow.
stacks was last and first. Fields are. So there's slight difference. She's gonna tell you.
Just to give you guys a hint, right? Look at how similar these things look. Right? Look at how similar they are. Your implementation of Q should look almost identical to your implementation of stack. You're probably just going to use different array methods to NQ and DQ. All right. So I think that's just a bit more. This really makes sense. Yeah. Right? The way I think of it is By the way, if y'all are working on this and are like, I'm not sure how, if you guys are looking at this and you're having a moment where you're like, oh man, class notation, what's going on there? It's been a while since I've dealt with that, right? I think it's like a great opportunity for you to review classes to work on this, but also, right, review of class notation doesn't have to come at the expense of new material, right? If you look in CodeShare, right, I've shared a little challenge to make a tic-tac-toe game using the DOM, right? That incorporates both class notation, because it's basically just recreating the logic of the tic-tac-toe game, the class notation, and DOM manipulation. So that's an incredible opportunity for you both to bone up on what we've been studying really recently, and to get a pretty fulsome review of what classes are and how they work, right?
All right, on that note, I want to continue because I do want us to have an opportunity to do whiteboarding today. So, whatever, I'm loud enough, especially now that the microphone's working. All right, so how can we start this off? Who can help me here for Q? The first thing I gotta write, Nikki. Perfect. What should I call it? Yeah, sounds good.
Oh, this dot array
Okay. Perfect. Thank you. All right. So we got to write. What's our first thing we're writing? NQ. What's it take in? Okay. Which way should we go? How do we want to do it? Somebody else. Thank you, Nikita. I want to get more voice. If you haven't spoken today. Oh, nice. Thank you, Eric.
This array push out.
Sounds good. This array dot push the value. So we're going to go in this way, right? And so that means we're going to, on our DQ, when we're going to DQ, we got to go that way as well. So let's write our DQ. I don't know how to spell it. Okay. So what should, yeah, push me in. Depends on what we want to, if we want to. I don't want to return right now because I don't want to, JavaScript's return for default for push is the length of the array. I don't really want to give people that for this situation. If you wrote your own and you did, then that's fine too. Max? Cool. Probably should return this one. So we got a peak, right? We want to do. Where am I looking for peak now? Who can help me with this one? Where am I looking? Jackie. Okay. Return this dot array at the 0th index. Looks good. And last is empty. What's next? What's our last step? Who haven't I heard from today? Andre. Last step is empty.
Basically, I'll go with bang operator, bang this
Bang, bang.
Oh, one bang.
That's going to give us the opposite. So if we did this and our length was 0, what would we get back? True. Oh, is that what we want?
Oh, wait,
Yeah, wait a minute. Maybe this is what we want. Maybe you're right. Because we would want, because if it's 0, we would want it to return true because our length is 0. So that's right. I'm mistaken. Which means we were wrong on the last example. Good one, Andre. Stepping up with the correction. Nobody caught on the last round, including me, so that's all right. Right, it would return true, but that would mean it's empty. Because is this empty? If the length is 0, we would want it to return true, as it is empty.
I have a question for the peak method. Do we have to return anything?
We want to see what the next element is. So we do have to return that. Great question. So do we have to return with peak? And I'm saying yes, because we want to be able to see it. All right, any other questions? All right, so just quick review. We have a stack, which is a LIFO, stands for, yeah, it's just like when you are sick and you eat something and then you throw up. All right, whatever's the last that just came in is what you're throwing up. And then we got our Q, which is FIFO, which is first down. Example of that is me at a nightclub. And that's it. That's stacks and queues. All right, the NQ, DQ, and we have push and pop, and then we also both share is empty and peak. Right?
Is there a philo?
First in, last down. That sounds a lot like a stack to me. Right? The opposites of these are still the same. Yeah.
The last one, you're
Yeah, the last one was incorrect. I made a mistake. Johnny,
so this is playing to recursive function.
this is not.
Like this actual.
Oh, because we build a stack. As every time a function call, it gets added to the stack, and we don't go to the next. We don't go back until that has resolved, and then that pops off the stack, and we go to the next one. All right. Yep. Yeah, that's a great question. So can we write NQ with unshift, he says. So if we do that, now it's coming into the front of the array. So how do we DQ? Yeah, we got a pop. And our peak is the next element that's going to go. So what do we have to do? Yep, same thing. Right, we don't really care which direction it is. We just care that it's a line. We don't even have to implement this with an array. That's what we know right now for under the hood. Someday we'll use linked lists, perhaps. Hint, hint, hint. Okay, so pair off and do some whiteboarding. Davey?
Please put someone available to that.
That was